All right, so a couple of important reactions with benzene. Let's just start off with some oxidations. So the most vulnerable part of the benzene is actually in the benzylic position. So you see it's not the benzene itself, but one position just off of the benzene, so right here. So these benzylic positions are susceptible for oxidation. So if we have Jones reagent or dichromate, basically we're going to be able to oxidize right here at that benzylic position. All right, so there's two reagents. You can either think of Jones reagent or any combination of these chromium reagents, or also, but not PCC because it's too mild, but if we have something stronger like chromic acid or sodium dichromate in acid, or potassium permanganate is also another really strong oxidizing agent that will just oxidize that position. And what I mean by that is it's going to cleave it. So see this long R group here? It's just going to break it off, and we're going to make a carboxylic acid there to replace the big R group. So same thing here. At this position, we'll get some oxidative cleavage, and we will end up with carboxylic acid there. All right, so maybe just to practice, I could have, something like an isopropyl benzene, and if I use KMnO4 or Jones reagent and heat and just oxidatively cleave it. So doesn't matter how many carbons you have, it will just cleave them off and you'll end up with one. All right, now this H here is in basic conditions, which is what we usually use for potassium permanganate. You won't have the H there, but after an acid workup step, you'll have the H. So we usually do like a step 2 H3O+, just to get it in its neutral form. All right, so just practice with this a little bit. It is a reaction that you occasionally see with synthesis. This one is no reaction because it's tertiary. So in order to have oxidative cleavage, you have to have a CH bond there for oxidation. So it doesn't work so much with tertiary. You have to have a CH bond present in the benzylic position for this to work. All right, so let's practice with that. I'd like you guys to take a look. If you use benzene and you use these reagents, Na2Cr2O7, it's a sodium dichromate, what will be the product that you get at the end? Okay, so for each one of these, basically as long as you have an H present right here, a benzylic hydrogen, you can do an oxidative cleavage. And this is sort of related to the idea of the alcohols. You remember how with a tertiary alcohol you couldn't oxidize it to a ketone because it'd have too many bonds on it. So you can only do oxidation if you have a CH bond because those are more susceptible than a CC bond is to oxidation. Okay, so for that example, you're going to get benzoic acid. And then for this example, if you have excess sodium dichromate, you can oxidize both positions. So you can end up with dicarboxylic acid like that. So these are in the meta position, just to review that. Okay, so let's also review some of the reactions we've done before. So radical bromination in the benzylic position. I think you guys remember that was a special reagent, N-bromosuccinimide, NBS. And then we can oxidatively cleave it. So we can use Na2, we just used it, Na2Cr2O7, or you can just put Jones reagent if you want. Jones. That's just something some of us use. And then here, this is oxidative cleavage as well, so this is the same as that. Radical bromination, again in the benzylic position, that's NBS. So these are all sort of similar. All right, now once we have the benzylic position brominated, then you can do SN1 or SN2 and change it out with an alcohol group. So to do that, maybe use NaOH without heat to go for SN2 there. So that works. All right, and then here, SN1, you could try to get, maybe just do this reaction in water and have bromine leave as a leaving group and water attack. To do E1 elimination right here, you'll probably want to use H2SO4, concentrated H2SO4, and heat. That's going to favor elimination. So remember, this gets protonated, and then a base comes and water leaves after a pi bond is formed there. And then E1 to E2, we could have a strong base like hydroxide come and grab this H, form a pi bond, and then have the bromine leave. So that's an E2 reaction here. So just remember, alcohols, this was from chapter 12, alcohols chapter 12, alkenes chapter 8. So let's work through this synthesis and show all the intermediates that will show that we understand each step. So first I'm going to do NBS, that's allylic bromination, so that's right here. So I'm going to show Br here. So that's after the first step, NBS. Then I have NaOH. And so that tells me that my OH group is going to come in and do maybe a substitution. I don't see heat, so I'm not going to do elimination. Also, I can't really do elimination. There's no beta hydrogen to do an elimination. Okay, and then now that I have a primary alcohol, I just want to oxidize it to an aldehyde, not a carboxylic acid. So I'm going to use PCC, pyridinium chlorochromate. All right, so I hope you saw how we pieced all that together. So we're basically just using this map up here. So now let's try something similar on our own. So basically it's the same thing, right? So just see if you can try that again from scratch later on when you don't, when we didn't go over it. All right, 17, 18. Okay, so here are some ones to try then. So remember to try some of these strategies here, just to piece together things that we learned before, radicals and alcohols and alkene reactions. So let's do one of these together, and then you can do the other ones on your own. So let's do this one here. So I don't want to cleave it because I want to keep this isopropyl group. I just want to add an OH. I want to add an OH here. Before I add an OH, remember this is just an alkane, right? This is an alkane with an aromatic group. So basically need to brominate it. So I can use Br2 or I can use NBS because it's actually benzylic position. So I'm going to use NBS. It's going to be more effective for benzylic and allylic. And so after I do that, that's going to give me my bromine here. Okay, so then if I want an OH group, then this is tertiary, so I think I just want the bromine to leave, make a carbocation there, and then have an OH group attack. So it could be either in the form of sodium hydroxide or it could be water. Now I don't want sodium hydroxide maybe because it might do elimination. So maybe I'll just stick with water. So HOH or H2O. Just stick with water, and then when bromine leaves, I'll have water attack. All right, so go ahead and think about, okay, first making these R groups need to have some group on it. You want to add a functional group there. The easiest thing is probably bromination. So then think about how to eliminate or substitute after that. Okay, and then just real quick, once you brominate this one with NBS, then you can just do an elimination with a strong base. So let me show you that real quick. That'll be the second. So the first step here to here is just NBS again, and H nu, and again NBS because it's the benzylic position right there. And then if I take away this beta hydrogen with some sodium hydroxide, then I get the elimination E2 reaction. And then in part C, we're going to do radical bromination again, so NBS again, and H nu heat or light, H nu light. And then I'm going to have this alkyl halide, and notice I'm doing a little bit of retrosynthetic analysis here. I already have this one carbon, so I need to figure out how to get this group on there. And actually, that's a nucleophile. That's a cyanide. C triple bond N. It's got a lone pair on the C, so it can just attack here and release the bromine. So to get that reagent, cyanide, I can just put NaCN, sodium cyanide. All right, So that's a good review because we don't really use sodium cyanide a lot. We haven't been in practice, so it's probably a good idea to have that there. This reaction is not really that common to see, but if you just take benzene and you hydrogenate it, you need to add a lot of pressure and temperature. It needs to be hot because this is stable, so it's not really easy to react. So you usually see crazy stuff like this to try to get it to take on those hydrogens to saturate it. So it's not really that practical. I mean, if you want this, you just get that, right? You don't have to convert benzene into that. But anyway, it's just another demonstration that benzene is pretty stable. So you need a high temperature, high pressure reaction to make that happen. There's something called Birch Reduction, but I'm not going to focus on that. So just learn the reactions that we've covered so far, which is allylic bromination, review of your substitution elimination, strong base, and your oxidations, KMnO4, Jones reagent, things like that. And then finally, I left you with some pictures of buckyball or Buckminster fullerene, which is C60, and these are all aromatic compounds. They are 6-membered and 5-membered rings with conjugated pi systems. That these are actually used in today's world to develop really lightweight, very strong materials, so like carbon nanotubes, carbon fiber. You've heard of these, like people love riding bikes made out of carbon nowadays because it's so strong but also really light. So it's really exciting materials that can be made, and they show superconducting properties as well. So these are really interesting. This is what's called a carbon nanotube. So anyway, there are lots of different applications for these. You might see in aerospace or even like medicine someday. So anyway, they're really exciting to see. So I encourage you to just Google, graphene, buckyballs, or nanotubes and see what you get. All right, I'll see you guys at the next one.